Welcome to the Explainer. Today, we're diving straight into the engine room of the human body. We're going to explore exactly how our bodies manage, shift, and optimize cellular energy over a 24-hour cycle. We're basically looking at a biological day in the life. And let me tell you, it's an incredibly elegant system when everything is working the way it should. But right off the bat, I want you to think about a super relatable question. How does your body actually know whether to burn that donut you just had for breakfast or to tap into your stored body fat? It's something we totally take for granted, right? But this rapid cellular decision-making process is literally the core mystery of human metabolism. So to unravel this mystery, we're going to hit 5 key stops today. We'll start with what metabolic flexibility actually is, then look at the shift from fasting to feeding, how we fuel up for exercise, what happens when this whole system breaks down, and finally, we'll tie it all together with the circadian rhythm connection. All right, Section 1. What is metabolic flexibility? Here's our working definition for today. Metabolic flexibility is the ability to respond or adapt to conditional changes in metabolic or energy demand. Basically, how well you switch gears. And the origin of this term is actually pretty wild. It wasn't even coined for humans. Back in 1985, researchers used it to describe a parasitic worm called a Helminth. This little guy had the incredible capacity to switch between aerobic and anaerobic respiration just to survive environmental changes in its habitat. Fast forward to today, and we use that same concept to describe our own physiology's amazing adaptability. And here's what that adaptivity looks like in us. Notice how things shift around. Over on the left side, when you're sleeping or fasting, your skeletal muscle, represented by the red icon at the top, is relying heavily on fatty acid oxidation. Meanwhile, your fat tissue, those yellow clusters, is actively breaking down lipids to supply that fuel, which is a process called lipolysis. But then shift over to the right. When you eat a meal, the whole system flips. Your muscle ramps up glucose oxidation and glycogen storage, while your fat tissue hits the brakes on lipolysis and switches into storage mode. And right down at the bottom, from rest to exercise, you see the system adopting yet again to meet some truly massive energy demands. Moving on to Section 2, the fasting to feeding shift. Think of this as your metabolic morning routine. The absolutely crucial takeaway here is just the sheer efficiency of this transition. In the fasted state, your skeletal muscle is burning fat, clean and simple. But the exact moment you eat a meal, insulin hits the system. That insulin spike is the major driver shifting your body from a catabolic, breaking down state, straight into an anabolic, storing state. Your muscles rapidly dial down the fat burning and aggressively start oxidizing the glucose from your food, packing away the excess as glycogen. At the exact same time, the release of fat into your bloodstream is rapidly shut down. It's like flipping a switch. Which brings us to a massively underappreciated organ, white adipose tissue, or WAT. For decades, we kind of just thought of white fat as an inert storage bin for extra calories. But the source material makes it abundantly clear that this tissue actively orchestrates your fuel flux. It is insanely sensitive to insulin. When you're fasting, it perfectly buffers and releases free fatty acids to feed your peripheral tissues, like your muscles. When you eat, it undergoes massive reesterification, safely tucking those dietary fats away. Get this, a completely healthy normal weight woman can actually have just as much white adipose tissue as an obese man with type 2 diabetes. So the issue isn't always the amount of fat you have, it's whether that fat tissue is metabolically adaptable and healthy enough to orchestrate this complex fuel switch. Section 3, fueling up for exercise. Let's look at the workout shift. When you go from just chilling on the couch to exercising, your body's energy demands can skyrocket by up to 25-fold. It's intense. Look at the data comparing trained athletes to untrained subjects when they're given a massive acute lipid overload, which is basically an IV drip of pure fat alongside insulin. In the middle panel with the yellow bars, you can see the trained athletes have a vastly superior ability to ramp up fatty acid oxidation to handle all those extra lipids. And because they're burning that fat so efficiently, if you check out the red bars on the far right, they actually preserve their precious muscle glycogen stores. The untrained subjects, they simply lack this metabolic flexibility. Their cells just get gridlocked. You also have to remember that exercise intensity and duration dictate where your fuel comes from. As you push into really high-intensity exercise, your body increasingly relies on glucose and anaerobic glycolysis. But if you extend that run or bike ride into a long duration, fatty acids step up to carry the load. And here is the coolest part. Exercise is a powerful activator of AMPK, which is basically the master energy sensor in your muscle. Chronic exercise literally induces changes at the gene and protein level. Simply put, Working out literally remodels your cellular machinery so you have better metabolic flexibility for your next workout. It's a real game changer. All right, Section 4, When the System Breaks. Welcome to Metabolic Gridlock. So this is what metabolic gridlock looks like in the data. On the left, we're looking at how well the body suppresses free fatty acids under insulin stimulation. Healthy, active people, no problem. Their fat tissue listens to the insulin. But look at the tall dot representing patients with type 2 diabetes. They have a severely blunted ability to suppress those fatty acids. Their fat tissue is resistant. Now, over on the right, we're looking at how well fat tissue absorbs and releases nutrients across 3 meals in a single day. The blue line is a lean individual, showing these really dynamic, healthy spikes of fat storage right after each meal. The red line is an obese individual. You can clearly see their fat tissue progressively failing to store fat effectively after those meals. The tank is just full and the system is flat out refusing to adapt. And this brings up a highly provocative scientific idea from our source material. What if insulin resistance is actually an adaptive defense mechanism? I know, we usually think of it as purely pathological, a disease state. But consider this. If your insulin signals are disrupted or constantly oscillating, your white adipose tissue might purposefully develop resistance just to make sure it keeps releasing the free fatty acids that your heart and muscles desperately need to survive during a fast. It's a really fascinating perspective, showing how our bodies try to protect us even when the broader system is failing. To see the real-world consequences of this broken system, check out this data from a 24-hour metabolic chamber. It measures the respiratory quotient, or RQ. Basically, a lower RQ means you're burning fat, and a higher RQ means you're burning carbohydrates. The blue line is a healthy volunteer. Notice how beautifully dynamic that line is? It spikes high to burn carbs after breakfast, lunch, and dinner, and then drops into a deep valley of pure fat burning while they sleep. Now look at the red line. That's a patient with type 1 diabetes. The line is rigid, it's flat, and it's elevated. They lack the flexibility to transition efficiently between fuel sources during meals, exercise, and sleep. Finally, Section 5, the circadian rhythm connection, tying sleep and metabolism together. The American Heart Association puts it pretty bluntly with this quote: "Human physiology is partially regulated by the circadian system, which produces approximately 24-hour rhythms adapted for daytime activity and nighttime rest." Listen, our metabolic flexibility isn't just about what we eat or how we move. It is deeply, inextricably linked to the time of day. Disruptions to our natural circadian system directly contribute to cardiometabolic dysfunction and drive the progression of disease.
So, what are the keys to maintaining circadian health? It's all about aligning your internal system to the external light-dark cycle to keep everything in balance. And here is the absolute kicker. Getting 8 hours of sleep is great, for sure. But keeping your sleep timing perfectly regular is just as important as the duration of your sleep for keeping your metabolism flexible. Going to bed and waking up at wildly different times on the weekend totally confuses your cellular clocks. It disrupts that beautiful daytime feeding, nighttime fasting rhythm we've been talking about this whole time.
Which brings us to the end of our explainer. I want to leave you with one final provocative question to ponder. Is your daily lifestyle making your cellular engine metabolically flexible, or is it leaving you gridlocked? Because every single meal timing, every workout, and every regular bedtime is a chance to train your cells to be as adaptable as possible. Thanks so much for joining me on this deep dive into the science of metabolism.